Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second in a series of short videos on basic electronic circuit analysis. In the first video, I covered Ohm's law. In this second video, I'm going to cover the first of two foundational laws that apply throughout electronics, Kirchhoff's current law. If you find this video helpful, please click on like and subscribe so that you will be notified when new videos come out. When people hear about Kirchhoff, the first thing they think is that somebody coughed. Kirchhoff! This law was named after a real guy in the 19th century. His name was Gustav Kirchhoff. He was a Russian-born German physicist. Kirchhoff's current law, or KCL, is the first of Kirchhoff's laws, announced in 1865. It states that the algebraic sum of the currents entering a circuit node must be equal to 0. Well, what on earth does that mean? Well, let's take a look at this on the whiteboard and find out. So, Kirchhoff's current law states the algebraic sum of the currents entering a node must be equal to 0. So, what is a node? Well, it's not that thing in the middle of your face. I get a node. A node is a junction in an electrical circuit. Wherever two or more things connect at one point, this is a node. So you have a wire coming in here, and you have a connection point and a wire coming out here. This here is a node. Now, the key to understanding what this means is noticing the word entering a node. So, what we then say is, well, if current is entering a node, here we have some current coming in here. We'll call that I1. Now, think about this. If we have current coming in, current is electrons moving through a wire. And if you have electrons moving through a wire, is it possible for there to be fewer electrons coming out this end than are going in this end? It's like a water hose. If you have water flowing through this hose, the same amount of water is coming out one end of the hose as is going in the other end of the hose. Same thing here. Otherwise, your hose would blow up. It would just get bigger and bigger and bigger and bigger. And the same thing here. So that means that in this particular case, current 2 has to be the same as current 1 because there's no other place for it to go. But current 2 is exiting a node. So we can say that current 1 is positive current because it is entering the node. Current 2 is negative current because it is exiting the node. So if I1 is equal to 2 amps, then I2 has to be equal to minus 2 amps. And algebraic sum, so 2 amps plus a minus 2 amps is the same as 2 amps minus 2 amps, which, by the way, is a big fat 0. All right, now let's consider a little bit more complex situation. Suppose now we add another wire to our situation here. We now have current coming here. We'll call this, just like before, I1. We have current going out here. This is I2. And we have current, in this case, going out here. We'll call this I3. Well, again, the electrons have to go somewhere. They can't bunch up in the middle of all of this stuff. So if we have I1 is 5 amps, so 5 amps worth of electrons are flowing into this node. That means that somehow the number of electrons coming out here and the number of electrons coming out here has to be such that it makes up 5 amps. And so if this is 2 amps coming down this way, now it's exiting the node, so that means it's minus 2 amps. This one is exiting the node, and because this is 5, we can say, algebraic sum, remember, 5 plus a minus 2, that's this guy here, plus whatever I2 is, must equal 0. So this is, here we say 5 minus 2, because this becomes a negative, plus I2 is equal to 0. 5 minus 2 is 3. 3 plus I2 is equal to 0. And then if we subtract 3 from both sides, so 3 from 3 gives us 0, plus I2 is equal to minus 3. So we now know that I2 equals minus 3 amps. And this is relative to this node. That's an important point. It's relative to that node. I2 is minus 3 amps if I3 is minus 2 amps and I1 is 5 amps. So let's consider another case here. What if we have current coming in from this direction, again, I1, and we have current coming in from this direction, I2. We now have current going out from this direction, which is I3, because you can't have all the current coming in. There has to be an out somewheres. And suppose this is 5 amps here. And suppose this is 3 amps here. And we want to find out what 3 is. Well, again, the algebraic sum. So we have I1, which is 5 amps, plus 3 amps, because this is going into the node, it's a positive 3 amps, plus I3 is equal to 0. 5 plus 3 is 8, plus I3 equals 0. We subtract 8 from both sides. 8 minus 8 is 0. So I3 is equal to 0 minus 8 is minus 8 amps. So there you go. This is Kirchhoff's current law. The algebraic sum of all of the currents entering a node must equal 0. So there you have the short and sweet of Kirchhoff's first law, also known as Kirchhoff's current law, or KCL. It is the second law that is the undercurrent beneath all circuit analysis. In the next video, we'll be talking about Kirchhoff's voltage law, or his second law. If you found this video helpful, be sure to click on like and subscribe to this channel. Thank you for watching, and until next time, toodaloots.